The inaudible whisper of the cosmos, the near-mythical passage of the neutrino, forms the bedrock of a narrative far stranger and more profound than any simple assertion of extraterrestrial biology could ever achieve. To postulate life constructed from these phantoms, these near-massless entities, is to venture to the very edge of known physics, a frontier where the standard model strains against the limits of our imagination. We begin, as any rigorous inquiry must, not with fantasy, but with the hard, cold reality of the constituent parts, tracing the lineage of the neutrino from the heart of thermonuclear furnaces to the silent detectors buried deep beneath ice sheets and granite. Consider the context. The Standard Model, that towering edifice of particle physics, lists the neutrino as a fundamental fermion, one of the 12 essential constituents of all known matter, yet it behaves with an almost deliberate aloofness. It possesses no electric charge, rendering it immune to the electromagnetic force that sculpts atoms and dictates chemistry, the very force underpinning the carbon bonds that define Terran life. Its mass, once theoretically zero, is now confirmed, thanks to the Nobel-winning discovery of neutrino oscillation, to be minuscule, perhaps on the order of 1/10,000,000th of the electron's mass, defined by the precise, though still vaguely bounded, range between 0.060 electronvolts squared over the speed of light squared and 0.161 electronvolts squared over the speed of light squared for the sum of the squared mass differences. This near weightlessness, coupled with its exclusive interaction via the weak nuclear force and gravity, means that for every cubic centimeter of space we occupy, approximately 300 neutrinos, relics of the Big Bang itself, streak through our very being, unfelt, unheeded. The very question, the notion of a neutrino-based biology, demands a radical re-evaluation of what life entails. On Earth, life is inherently an electromagnetic phenomenon, a dance orchestrated by the attraction and repulsion of charged particles. DNA, the blueprint of existence, relies on hydrogen bonding, a purely electrostatic interaction. Proteins fold into specific three-dimensional configurations dictated by the subtle interplay of charged residues and hydrophobic forces, all mediated by photons, the carriers of electromagnetism. For a neutrino, an entity that slips through the macroscopic world as if it were not there, to construct a stable, self-replicating structure capable of evolving, this is the hurdle that turns compelling science fiction into nearly impossible physics. The weak force, the only other fundamental interaction neutrinos readily engage in, has an interaction range so infinitesimally small, estimated to be around 1/10,000th the diameter of a proton, that building anything larger than an ephemeral, quantum cluster seems inconceivable. Imagine trying to build a skyscraper not with bricks held by mortar, but with wisps of smoke that only occasionally, once in an eon, briefly touch one another before vanishing back into the ether. Entropy, the relentless drive towards disorder, would instantly dismantle any nascent neutrino aggregate. Yet, the very scarcity of their interaction is what lends the neutrino its cosmic dominance in terms of sheer numbers. They are the unseen ocean upon which the islands of baryonic matter float. To explore the possibility of neutrino life, we must pivot to the theoretical frameworks that dare to step outside the confines of the carbon-water paradigm. Astrobiology, in its most speculative corners, often entertains alternatives: silicon chemistry, which offers weaker but potentially more stable bonds than carbon under extreme conditions, or perhaps exotic solvents like liquid ammonia or methane in the frigid hydrocarbon seas of Titan. Even concepts involving exotic matter, like life existing within the complex structures of dark matter clumps, are often hypothesized to rely on some form of self-interaction governed by the as-yet undiscovered dark matter force. The neutrino, however, lacks even this potential for self-interaction beyond the gravitational, which is catastrophically weak at the particle scale. To formalize this impossibility, one must consider the energy scales required for biological processes. Biological information transfer, whether replication or metabolism, necessitates processes occurring on timescales far slower than femtoseconds, allowing energy states to be defined and manipulated. If neutrino structures were to exist, their internal dynamics would be governed almost entirely by the weak interaction cross-sections. The probability of two electron neutrinos scattering off one another, even given their immense population density, remains so vanishingly small that the time required for any meaningful information exchange or structural maintenance would likely exceed the current age of the universe, which stands at approximately 13.8 billion years. The conceptual leap required for neutrino life necessitates inventing a new fundamental interaction, one that specifically governs neutrino-neutrino attraction or bonding, bypassing the limitations imposed by the Standard Model, a hypothesis for which there is currently zero empirical support, despite decades of painstaking particle accelerator experiments at facilities like CERN's Large Hadron Collider, which tirelessly probe the high-energy limits where new forces might manifest. However, the neutrino's true mastery over the universe lies not in hypothetical biology, but in its essential role in cosmic asymmetry, the very reason we have a universe to be alive in. This brings us to the profound mystery of baryogenesis, the mechanism that allowed matter to triumph over antimatter after the Big Bang. Early universe thermodynamics predicted a near-perfect annihilation. For every particle of matter, there should have been an antiparticle, resulting in a sterile universe dominated by radiation. The slight imbalance, the one part in several billion that tipped the scales toward the existence of protons, neutrons, and eventually atoms, is a critical ingredient for our reality. Neutrinos, with their peculiar quantum mechanical properties, are prime suspects in this cosmic accounting error. Specifically, the concept of the neutrino being a Majorana particle, meaning it is its own antiparticle, is central. If the neutrino is a Majorana fermion, its decay or interaction patterns could introduce the necessary CP violation, the asymmetry between matter and antimatter interactions, required by the Sakharov conditions for baryogenesis. Experiments are relentlessly hunting for this signature. The search for neutrinoless double beta decay, for example, is a direct test of the Majorana hypothesis. Detectors like the German-led Katrin experiment, while primarily focused on measuring the absolute mass scale, contribute to the overarching picture. More explicitly, massive underground observatories like the Japanese Hyper-Kamiokande project, or the already operational Kamlanzen experiment, are designed to spot this extremely rare decay, where an atomic nucleus emits two beta particles without any intervening neutrino emission, a process only allowed if the neutrino involved is its own antiparticle, effectively cancelling itself out. If confirmed, this would confirm the neutrino's role as the architect of matter dominance. Imagine this profound irony: the particle that can never form life is the very particle whose properties ensured that any life, based on conventional matter, could exist at all. It is the silent guarantor of our existence, not its inhabitant. Furthermore, the sheer information content carried by neutrinos, though inaccessible to biological systems, is invaluable to astrophysics. Neutrinos stream directly from the core of supernovae, unimpeded by the opaque plasma that traps photons for millennia. When supernova 1987A exploded in the Large Magellanic Cloud, detectors across the globe, including those buried in the Gran Sasso Laboratory in Italy and Kamiokande in Japan, registered a faint but unmistakable burst of neutrinos. This direct observation provided the first real-time data on the mechanics of core collapse, confirming decades of theoretical models regarding the energy budget of these stellar death throes. In a universe where light is easily scattered or absorbed, neutrinos are pure, unadulterated messengers from the most violent events. Telescopes like the IceCube Neutrino Observatory, deployed in a cubic kilometer of Antarctic ice, are now mapping the high-energy neutrino sky, identifying astrophysical accelerators, blazars, and active galactic nuclei that hurl these particles across intergalactic distances. These IceCube detections, often correlating with observations from traditional electromagnetic telescopes like those managed by the National Radio Astronomy Observatory, offer a multi-messenger astronomy that illuminates the universe's darkest corners. Returning to the concept of exotic life, one must confront the constraints imposed by thermodynamics and information theory. Living systems require a pathway for negative entropy, a mechanism to locally decrease disorder by increasing the disorder of their environment, the crucial element of metabolism. Even if a neutrino structure could somehow maintain coherence over geological timescales, what would its metabolism look like? It would require harvesting energy through the weak force, perhaps by forcing a near-simultaneous interaction between two neutrinos to produce a W boson, which would then decay into charged leptons, depositing a minuscule amount of energy. The probability of this occurring in a controlled, cyclical manner necessary for replication is statistically negligible. Compare this to the efficiency of photosynthesis, where chlorophyll molecules, interacting via electromagnetism, capture the energy of a photon, an electromagnetic particle, with quantum efficiency, driving the synthesis of complex carbohydrates. The neutrino bypasses this fundamental machinery entirely. The discussions that arise in forums, often among amateur theorists or those exploring the fringes of speculative physics, often miss the crucial distinction between abundance and structure. A large population does not equate to organized complexity. Consider the immense sea of virtual particles that constantly pop in and out of existence in the quantum foam, governed by the Heisenberg uncertainty principle, which permits energy fluctuations over brief time intervals. Neutrinos, being real particles, are not merely virtual fluctuations, they possess conserved quantum numbers and definite, albeit small, masses. While the vacuum is teeming with potential interactions, the lack of a mediating strong or electromagnetic force for neutrinos renders the construction of anything resembling a stable information polymer, the neutrino equivalent of RNA or protein, a structural impossibility under known physics. If one were to propose a structure, perhaps a tightly bound, transient state achieved only under extreme gravitational conditions, like the singularity of a black hole, the very environment that might enforce temporary cohesion would simultaneously destroy any discernible organizational principle through tidal forces and Hawking radiation. Furthermore, the concept of a neutrino-based organism implies a form of sentience or complex processing. Even if we stretch credulity to allow for the temporary formation of complex neutrino clusters, the mechanism for information storage and retrieval remains entirely unexplained. Biological memory relies on precise, stable physical configurations, the sequence of bases in a DNA strand, the precise folding of a prion. A neutrino structure, interacting only weakly, could not maintain the necessary fidelity across generations. Any information encoded would be instantly scrambled by the slightest environmental perturbation or the inevitable, random scattering event. This leads to a deeper philosophical point often debated in astrobiological circles, the substrate independence of life. While life might theoretically be substrate independent, it must still be system dependent, meaning it must utilize the strongest available interactions relevant to its environmental niche to build complexity. For any known environment, this means electromagnetism is paramount. Neutrinos exist in an environment where electromagnetism is irrelevant and the weak force is too short-ranged to build macroscopic order. To further expand the discussion into potential observational windows, we must consider what the neutrino equivalent of a SETI signal might look like. Terrestrial SETI projects scan for narrowband radio transmissions, the unmistakable signature of artificial electromagnetic manipulation. A neutrino-based civilization would not broadcast in radio waves, they would manipulate the neutrino flux itself. Such manipulation would require generating highly coherent beams of neutrinos, or perhaps inducing specific, non-standard oscillations patterns across vast distances. Experiments like the Deep Underground Neutrino Experiment, or DUNE, designed to study neutrino oscillation over baseline distances of thousands of kilometers, are highly sensitive to minute deviations in expected oscillation probabilities. If a civilization were actively manipulating the flux of muon neutrinos sent from a source, creating a patterned distortion in the electron-neutrino appearance rate at the detector, this might register as an anomalous signal. However, current searches are focused on understanding fundamental physics parameters, the mass hierarchy, CP violation, and detecting any signal suggestive of artificial manipulation would require sensitivity orders of magnitude beyond current technological capability, coupled with an absolute certainty that no natural astrophysical source could mimic the signal. The current detection limit for coherent neutrino beam events is essentially zero. The energy required to artificially induce neutrino interactions on a macroscale is another prohibitive factor. To generate a detectable, artificial neutrino beam capable of transmitting information across interstellar space would demand energy expenditures approaching the total output of a star. While advanced civilizations might harness stellar energy, directing this power into generating coherent neutrino pulses necessitates technologies that manipulate the weak force with precision that dwarfs our current understanding of nuclear reaction engineering. Compare the energy density of chemical bonds in biological molecules to the energy carried by a single neutrino event in a detector. The latter is vastly higher, but its probability of occurrence is astronomically low. A neutrino lifeform would need a metabolism based on harvesting these low-probability, high-energy events in a continuous, controlled feedback loop, a concept bordering on perpetual motion relative to the available interaction channels. Let us delve deeper into the implications of the neutrino mass measurement. The precise determination of the electron neutrino mass by Catrin, which yielded an upper limit of less than 0.8 electronvolts over the speed of light squared, though the more refined consensus from cosmological data and oscillation experiments favors the much smaller bounds mentioned earlier, is crucial. This mass is what allows oscillation to occur, transforming, for instance, a neutrino created as an electron type into a muon type en route to Earth. This mixing of states is a quantum mechanical phenomenon entirely divorced from the macroscopic organization required for life. If life were possible based on these particles, this mixing property might be exploited for rapid, non-local information transfer across the organism's structure, perhaps replacing the slow diffusion of ions across a cell membrane. However, the rate of oscillation is dictated by the mass differences, which are small and fixed by fundamental physics. It would be a static form of communication, not the dynamic, adaptive signaling network that characterizes biology. Any thought or action would be predicated on the probabilistic tunneling between mass eigenstates, a process too sluggish and unpredictable for rapid cognitive function. Furthermore, the astrophysical context must be emphasized. Neutrinos are constantly bombarding us from every direction, predominantly from the Sun. The solar neutrino flux is immense, yet it has no bearing on our biological processes because the interaction cross-section is so small. If life relied on this background flux, every organism would need to be a gigantic, highly sensitive weak interaction trap, requiring an improbable density of target mass, perhaps a hypothetical biological structure composed of an incredibly dense, stable isotope optimized for weak interaction capture, and still, the resulting energy harvest would be insufficient to overcome the inherent thermodynamic noise. The standard biological imperative is to create ordered states by exploiting readily available, high-probability interactions, like photon absorption or chemical redox reactions. Exploiting the weak force is the equivalent of trying to win a lottery by waiting for a random, extremely rare quantum fluctuation to deliver the prize directly to your hand. The exploration of alternative life often touches upon the concept of sterile life forms, those that exist in environments inhospitable to baryonic matter, such as the extremely high-energy plasma near an accretion disk around a black hole, or the degenerate cores of white dwarf stars. Even in these extreme niches, life, if it arose, would likely rely on the surviving strong and electromagnetic interactions, perhaps forming highly compressed atomic structures or utilizing degeneracy pressure for structural support. The neutrino remains the outlier because it interacts minimally with the very environment it inhabits. A neutrino organism would be functionally decoupled from spacetime geometry in a way that conventional particles are not. It would effectively exist outside the established rules of local physical causality as we perceive them through macroscopic forces. In conclusion, the tantalizing hypothesis of a neutrino-based biology, while stimulating to the imagination and a testament to the human desire to find complexity everywhere, founders upon the bedrock of empirical physics. Neutrinos are the most numerous, least interactive particles, the cosmic dust motes that permeate all things. They dominate the particle count of the universe, serving as the silent proof of the Big Bang's asymmetry, ensuring that baryonic matter, the stuff of stars and life, exists in the first place. Experiments at facilities like the Sudbury Neutrino Observatory, which successfully measured all three neutrino flavors simultaneously, confirmed the solar neutrino problem resolution, solidifying our understanding of neutrino oscillation and mass. These discoveries underscore their role as fundamental probes of nuclear and astrophysical processes, not as substrates for biological organization. The vast, persistent stream of cosmic neutrinos pouring through our bodies daily serves as a powerful, albeit non-biological, reminder of the universe's true underlying structure, a reality dominated by near-invisible, fleeting entities whose collective influence is the prerequisite for all observable phenomena, including our own questioning existence. The search for life will continue to focus on chemically rich, electromagnetically interactive environments, leaving the neutrino to its essential, ghostly work of governing the cosmic balance, forever outside the realm of the living.